Yesterday in our lesson of the autoionization of water, we talked about a water molecule once in a while colliding with another water molecule and kind of showing the molecular geometry. Hang on. There, it catches up. Showing the molecular geometry of a bent molecule of water. When it comes into contact with just the right orientation, with just enough kinetic energy, we cause a bond to break. That bond releases this proton on a water molecule, which attaches to the electron domain of an oxygen molecule on the other water. What we're looking at is the formation of some acid ions known as hydronium, the addition of a proton, and the hydroxide ion, what remains after the original water lost its proton. The acid hydrogen ion, or hydronium ion, and the base hydroxide ion, we call those the acid-base ions. If we think about an equilibrium that sets up with this particular compound, an equilibrium says that we produce the ions of hydronium and hydroxide, and of course we're going to produce even amounts of the hydronium and hydroxide, the acid and the base ion. We come up with what's called a Kw, the ion product constant for water. Kw is the ion product of the acid and the base ion. You know, when we write our equilibrium, we always drop out pure solids and pure liquids, so the two reactants here, the liquid waters, we don't write about those as we would in any other reaction as well. We said that this comes out to be a constant, 1 times 10 to the negative 14th. You can see that being the top of our pH scale. And if I create equal amounts of hydronium and hydroxide, we solved yesterday that these would have to come out to be exactly 1 times 10 to the 7th molar units. The ion product constant for water identifies the pH scale, 7 being neutral and 14 being the top of the scale. And that's really the next steps in today's lesson, is just trying to take a look at those powers of 10 and putting them into a logarithmic function known as the pH scale. We like to use the pH scale because it takes those small values, 1 times 10 to this, and puts them into whole numbers between 0 to 14. The pH scale is a logarithmic function, putting a number that's quite small in terms of concentration units of acids and bases, and puts them into a more manageable number to think about 0 to 14. So it's a convenient scale to turn small numbers into whole numbers. As the pH decreases, the hydrogen ion actually increases exponentially. Now let's make sense of that. If the pH scale is just a numbering system to tell me how acidic or how basic a solution is, it goes from 0 to 14, with 7 having the exact amount of hydrogen ion as the hydroxide ion. We call that a neutral solution. We know those would be 1 times 10 to the negative 7th. That power here on the exponent tells us the logarithmic value on the pH scale of 7. When I go from a pH of 7 to a pH of 6, I've actually moved the exponent by a power of 10. pH of 6 is 10 times more acidic than a pH of 7. Something with a pH of 5, it's 2 numbers on the decimal line, it's 100 times more acidic than a pH of 7. And so forth. A pH of 4, 1,000 times more acidic than a pH of 7. That's the power of 10 in a logarithmic function. So even the slightest swing of pH, it might seem small, 7.4 being the pH of blood, although 7.0, too acidic, 7.6, too basic. That homeostatic mechanism of maintaining a pH of blood at 7.4, we have a lot of buffers in our body like bicarbonate and ammonium. Those buffers really work hard at preventing a swing of our pH, because even the tiniest number change is actually quite significant because those values are representing exponents, the power of 10. When we report pHs, there's an AP chemistry rule that we all agree to report pH with 2 decimal places. Regardless of how many sig figs are actually in the problem, we report always 2 significant digits, even if it's a whole number. If I were to take negative log of 1 times 10 to the negative 8th, the pH would come out to be exactly 8, but I'd report that as 8.00 pH units. So 2 significant digits, which just is saying 2 decimal places on any pH, even if it includes a 0 in the last place. Another relationship we should be familiar with is taking the negative log of hydroxide ion to find something called pOH of our solution. Some really good relationships, just kind of reviewing our first year chemistry course. And I think I'll write these bigger so I can, and I got that crowded in this area. So I'm going to just turn my paper onto a clean sheet. It says we have a relationship between Kw, the ion product constant for water, showing the acid ion in H plus or H3O plus, they are indeed the same, multiplied by hydroxide ion. And that's our value for the equilibrium of the self-ionization of a water molecule. Water will self-ionize to create 2 ions. And we know that's a constant, 1 times 10 to the negative 14th. Let's take the negative log of Kw and set that equal to the negative log of H plus and OH negative. Now when I negative log, that's a math term called P. pH, pOH, pKa, pKb, pKw. Anytime you hear that little P, it's a mathematical thing. It's not really chemistry, it's math. That means negative log. So negative log Kw equal negative log H plus times OH negative. I'm just taking the negative log of each side. Now algebra also shows for us when we have a negative log of 2 things multiplied, to separate them, we actually add them. So I'm going to distribute the negative log through both of those hydrogen ion and the hydroxide ion. Negative log of Kw now is known as pKw. That's just by definition of a mathematical relationship. Negative log of H plus is now called pH. And the negative log of hydroxide is now called pOH. If we negative log a constant Kw, the negative log of 1 times 10 to the negative 14th, that's the constant called Kw, is 14. If we literally hit that out, we could prove it to ourselves. Whoops. Oh, I transferred. I think that was to Ashley. Oh, somebody came in and asked me for the quad formula. Was it Ashley earlier? Was it? Oh. All right, so quit. If we negative log 1e negative 14, see how it's just showing us the power of 10 comes out to be exactly 14. So that's a constant, pKw, 14. And we can see that it results in giving us the sum of the pH and pOH. And that was a poster that used to hang in our room. It'll be up later in the spring for regular chem class. Top of our pH scale, if I know one value, I can easily turn it into the other. Knowing 14 minus either of the two can find me the other value. If I think about another relationship and just the power of 10, and you might want to just put this in the margin, I don't think I have a spot for it. If I wanted to turn a hydrogen ion concentration out of a pH, that formula would be 10 raised to the negative pH. It's kind of manipulating the log formula. And the hydroxide ion concentration can be found by taking 10 raised to the negative pOH. So pH, pOH, hydrogen ion, and hydroxide ion. If I have just one value of any of those 4, we can easily determine the other 3. And the relationships all just lie with the ion product constant, that whole talk about water ionizing to give us equal quantities of hydrogen and hydroxide. So all of that I kind of put on a separate sheet of paper just to give myself plenty of room. We will, someday in the future, when we test over this chapter, be asked to do something very similar to that. Give you hydrogen, ask you to solve for the other 3. Give you pOH, ask you to solve for the other 3, and we'll practice just manipulating one of those variables into the other. Let's do a little pH practice problem, and Allie, would you like to be our first reader today? Just read for us about lemon juice.
The sample of lemon juice, the hydrogen ion concentration is 3.8 e negative 4 m. What is the pH?
Thank you. This is a nice easy problem. They gave us the hydrogen ion concentration directly. No trick at all. pH is found by just simply taking negative log of the provided value, 3.8 times 10 to the negative fourth. Just kind of a plug and chug. Anthony, would you like to hit with me, my first calculator buddy? Let's solve for pH. Nicely done. And good work with the 2 decimals. And no units on a pH, are just called pH units. That number makes sense to me. Lemon juice is acidic. This is lying in the pH range of an acid. Makes good sense. Ready? Anika, would you pick up with the next little reading? Molar, yep. You know what? This is me being lazy when I type out my notepad. Instead of going times 10 and superscripting, I just write E. But they're right. That means times 10 to the. Alrighty. So a window cleaning solution, I'm going to suspect it's going to be a base. Ammonia is a good window cleaner. If it's Windex, that kind of thing, comes out to be a basic solution. So I'm just suspecting that we're going to have a number greater than 7 by the time we're done hitting. What's nice is they give me H+, so it's really just plug and chug into our pH formula. If pH is negative log of the provided hydrogen ion, little brackets stand for molar units. Let's hit out, and Riley, would you hit this one with me to be my calculator buddy? Perfect. Ashley, let's read a little bit about apple juice. Okie doke. Well, alright, apple juice will be acidic. If I want the hydrogen ion provided the pH, that's the 10 to the negative pH power. So we're going to hit 10 to the negative. Well, let me write that over. 10 to the negative 3.76. And Jesse, shall we hit together? I use the caret key for the times 10 to the caret there, negative 3.76. Beautiful. And that's a big M for molarity, the concentration of H+. Kyle, would you like to read what's next? Thank you. Yep. Alrighty, so we were given pH. We did 10 to the negative pH and found hydrogen ion. We have to find the other two guys. I think the easiest thing to do first is to find POH, and we'll just do that by a little subtraction trick. 14 minus the pH can pull out POH. David, would you hit that for us? 14 minus the pH. Thank you. Alrighty. 10 raised to the negative POH. We'll find our hydroxide. And Lydia, shall we hit that together and see what we find? Excellent. And that's a big M for molar units. Alrighty. Now, last year in Chemistry Land, we probably took a whole week practicing those skills, and we've just kind of reviewed those relationships in a little paragraph or two. The relationships between pH and POH, someday when we test, we'll have to find, given one, we'll pull out the other three, and it usually is done in kind of a table format. We'll take a look at a practice test example a little bit later on. Alrighty. In the laboratory, or even heck, we used to do this as a swimming pool owner. You'd often have to keep track of your swimming pool pH, or anybody own a hot tub, you kind of care about pH, don't you? There are certain gardeners care about pH. That's so not me, but people who measure soil pH. There's easy ways to find pH, and there's easy ways I think would be a nice digital pH meter. Oftentimes we use a pH meter if we need an exact readout of a pH, kind of with decimal points and so forth. We've used pH meters, and it's been a while in the lab, but they're one of our CBL attachments. They're calculator-based attachments. They have a glass bulb, and we have to keep them wet. They're an electrochemical cell, and they just measure ions swimming around in the water. So a pH meter is an electrochemical cell, gives you a nice digital readout, but probably more convenient and certainly more economical is just the simple use of an indicator can help us measure pH. Piece of litmus paper, right away with the dip we know if it's acidic or basic, with it turning blue for base or pink in acid. Phenolphthalein, clear in an acid, pink in a base. Remember when we're titrating, you want that faint pink color, overshooting and it turns dark pink and we're back to a do-over. So indicators are used if we just need to tell whether it's acidic or basic. If we need an exact, precise measurement, we're going to do a pH meter. When we start measuring the pH of solutions, we have to consider if we're measuring for strong acids or weak acids, strong bases or weak bases. To me, that's the difference between easy math or a little more complex math, setting up an equilibrium chart. Today's lesson is going to focus on strong. Tomorrow's lesson is going to focus on weak. Today's lesson is the easy math. Tomorrow we get to do the equilibrium problems. Tomorrow on the Moodle site if you're retesting. When I read the term strong acid, I go, oh, 100% dissociates. No equilibrium, no ice chart, just straightforward negative log. But I have to be able to recognize if it's a strong acid. When we first met each other back in September, we had a chapter called number 4 where we had to break apart the strong, leave together the weak when we wrote out ionic equations. We once had to memorize the 7 strong acids. When I try to go back, what I'm doing is staring at the periodic table, and that helps bring them over. I go to the halogen family, group 7A, fluorine, chlorine, bromine, iodine. The first one, fluorine, boy, is that nasty stuff. It etches glass. They won't even sell it to a high school. But it's not strong. It's not strong because the fluorine hangs on to the hydrogen. And the definition of strong means it 100% dissociates. Definition of strong doesn't mean that I can pour it all over my skin and not have anything happen to me. Hydrofluoric acid, some of the nastiest stuff, but it's not strong. Underneath it, hydrochloric, that's a 100% dissociated ion. Underneath that, hydrobromic, HBr, hydrobromic is strong, and so is hydroiodic. See these binary compounds? Hear that prefix hydro when we name them? Hydrochloric, hydrobromic, hydroiodic. Those are the 3 binary acids that are strong. Chlorine actually gets me 3 of them. Hydrochloric, plain old chloric from the polyatomic chlorate, perchloric, coming from the polyatomic ion perchlorate. So I've got hydrochloric, chloric, and perchloric. All those chlorine acids are strong. And one more, the nitric acid is also a monoprotic strong acid. That's what I have a scar on my hand from still, from getting a little nitric acid on. Bubbled the skin right up. These are all monoprotic strong acids. 100% of them dissociate when placed in water. There's one and only one diprotic acid, commonly called battery acid. It's sulfuric acid, H2SO4. Hydrochloric, hydrobromic, hydroiodic, chloric, perchloric, nitric are all monoprotic, and then the diprotic of sulfuric acid. What that means is when we're saying it's strong, 100% of it dissociates. So in my head, that means no equilibrium, that when I'm given the concentration of the acid, that tells me directly the hydrogen ion value. I don't need to do any kind of ice chart to figure it out. It 100% lies to the right of an equilibrium. So let's take a peek at one of these, just called a try these. Jessica, would you like to read for us? Thank you. Here's a word, whoops. Here's a word that just makes me smile. It says easy math in my head. Strong acid. Straightforward, where the pH can be found by the concentration of the acid. Perchloric HClO4 will 100% dissociate into its ions hydrogen and perchlorate. If we're given the original concentration of 0.4 molar of the acid and 100% of it produces ions, we know that these are indeed the same value. So given the concentration of the acid, what we're really given is the concentration of our acid ion. It's just a plug and chug. Negative log of 0.4 molar will pull out our pH of our solution. And BJ, would you like to hit with me and see what we find? I wonder if we should go up to 40, you think? Let's do that. Alrighty, so 0.40 pH units. Easy enough. Nate, want to read the next one? Thank you. Yay, it's one of the 7, so we'll start recognizing the yay part of that. No complex equilibrium charts. HNO3 belongs to the I'm a strong acid club, so 100% of it will dissociate when it forms its ions. Now pH can be used to find hydrogen ion, and in essence that's also telling us the acid. 10 raised to the negative 2.34 is going to give us hydrogen ion. And since it is strong, it's also telling us the nitric acid. Allie, would you hit with me 10 raised to the negative 2.34 and see what we find?
I wish I could, but my calculator ran out of battery power this morning.
Oh.
I have a calculator on my iPad, but it doesn't have enough little
Oh, yeah, you're right. They don't. They're not scientific. All right, thank you. Want me to throw one at you just for a later call on? I don't really mean throw, but I'm attached with a cord. There you go. Yeah. Oh, sorry. Anthony, would you be my calculator buddy? Let's hit for 10 raised to the negative 2.34. Thank you. And that's what I found. Strong acids, there's 7 of them, and that's what tonight's lesson will have you do. They're all strong, so you don't feel like there'll be a trick at all. All strong acids, all strong bases, just straightforward calculating, just a little review practice with pH formulas. Let's consider some POH when we talk about strong bases. There were 7 strong acids, and it says there's relatively few strong bases as well. And when I think about determining strong base, I don't really worry about memorizing because the secret lies right above our door over there on the solubility table. If I'm looking at the last name hydroxide, OH negative, that's what bases typically end with, and it's green for soluble on our solubility table, oh, that's a strong base. If it's red and I see a big old insoluble, well, I'm not going to consider that a strong base. It's not even dissolving in the water. So what types of first names who end with hydroxide actually dissolve? I think about my old CHOPS Na, those solubility, it's a silly little word, but CHOPS Na helps me remember the H in CHOPS are hydroxides. Typically they're insoluble. The Na part tells us that alkali metals and alkaline earth metals typically are soluble. So when I think about trying to determine what's a strong base, I go to that first family, lithium, sodium, potassium, rubidium, cesium. Those are the alkali metals. They're always soluble. I just want to make sure I spell that right on my paper. The OH negatives is a strong base, and the alkali metals, alkali metals are strong bases. So the alkali metals, LiOH, strong base, sodium hydroxide, strong base, potassium hydroxide, rubidium hydroxide, cesium hydroxide, those are all considered strong because they're soluble in water. Now it just says lithium, rubidium, cesium, especially rubidium, cesium. We hardly I don't even own any in the lab. Rubidium, cesium, very active alkali metals. Lithium is as well. Typically, if we're going to use a base, we're using sodium and potassium. The heavy metals of the alkaline earth metals I can also persuade to dissolve. Typically, we're going to look at strontium hydroxide and barium hydroxide, the heavier of the two alkaline earth metals. The very bottom two, now radium, of course, we don't own any radium, it's radioactive. Strontium, barium, those are the bottom two. It's calcium that's kind of that question mark. And if you look at my solubility table, it's just above the door. If you look at calcium hydroxide, isn't it that mustard color or caution yellow or whatever color? It's like, is it soluble? It says it's slightly soluble. So do I break it apart or leave it together? Well, that really depends on the conditions. It's like, if I take some really, really, really hot water and I get my stir buddy going and stir it for a long time, I can probably get it to dissolve. But if I just take a little plop of calcium hydroxide into ordinary tap water, it's going to sit there and float and not dissolve. So calcium hydroxide is slightly soluble. And I've seen people who have instructed their students to say, never break it apart. And I've heard people who say, well, always break it apart because you can get it to dissolve. And I know the AP board lets it go either way. So on your AP exam, if you're taking it and decide, oh, I'll break it apart because it's strong, or I'll leave it together because it's weak, they accept either answer because it's slightly soluble. So who's strong? Anybody whose first name belongs in that first column. Those are always strong, 100% dissociate. And the bottom two heavy ones, strontium, barium, and then calcium if the conditions are right. Alrighty. Now, those are the guys who end with OH negative as their last name, and that just goes by solubility rules. There are some other guys that act as strong bases as well. Let's take a look at some other examples. It says strongly basic solutions can be created with hydroxide ions, and most commonly we use an oxide to do so. Now, I showed this the other day and talked about the spectator ion and get rid of it when you consider the chemistry. I mean, the oxide has to have a first name. Usually it's sodium or lithium oxide. We have some of that in the lab. Calcium oxide is quite readily available. Calcium oxide, these oxides, they have an industrial use. I know one of the most common uses in the industry, they take potatoes, like fresh from your garden potatoes, and if you want to turn those into potato flakes, like I would cook them, you would need like the Insta potatoes. Well, who's going to peel all the potatoes to create the powdered form of a potato? They do so by just sitting there and dissolving them into sodium oxide or potassium oxide solutions. Taking a potato and just letting them soak overnight in that strong base, and the peels just come right off with a little water spray. Who knew that industrially nobody sits there? Little children in China don't have to peel the potatoes anywhere. You just use a chemical and they peel them right off with a little water. Yeah, I didn't mean to give that visual, but somebody has to peel them. When we think about oxide, it has to have a first name, but we're going to get rid of the first name and just consider the chemistry of the oxide ion. If oxide is placed into water, H2O if you want, we cleave off that hydrogen ion and we produce two punches, two hydroxide ions in that conjugate pairing. So with one water molecule reacting with an oxide, we actually produce twice the base ion, OH negative and OH negative. I think we wrote that a couple of times the other day when we were hooking together conjugate pairs. Oxide's conjugate, hydroxide. Water's conjugate is also hydroxide. So when I think about how much base comes out in pH, we have to remember to double that concentration. Let's do an example looking at an oxide and how that would play a role when determining pH. Anika, would you like to read for us a little practice problem on the top of page 7? Thank you. So sodium oxide, but I don't care about the sodium, it's going to be a spectator. So I'll just write about the oxide when I consider the chemistry. When I place it into water, it 100% dissociates, stealing a proton from the water to produce a hydroxide and a hydroxide. The moral of the story is for 0.01 molar oxide, I'm actually producing twice the quantity of OH negative. Neat. Absolutely. Yep. As a matter of fact, you'll see that written in the book that way as well. And you'll see me do it this way is just for conjugate pairing. That's all. But you've just done the math for us. We're going to have to double the concentration of the original oxide to find the concentration of the hydroxide ion. So you're right. We have 0.02 molar hydroxide value. So twice the value because we produced twice the number. So right there we've got 0.02 molar. But if I negative log 0.02 molar, we get something called the pOH. So a little flip at the end there to find its pH. Let's ask Riley, would you like to hit for the pOH with me and see if we get a common answer?
I have a question.
Sure.
Just leave it as 1.69 or would you round up to 1.7?
I would do the 70 because that looks like it should round up. Yeah. I'll do that. 1.70. Thank you. Almost there. Ashley, can you do that old 14 minus trick and share with us the pH of our solution? I did, yeah, the 1.7. Thank you. And I'll put on that 0 to give 2 decimals. So we had the hydroxide concentration as 0.02 molar. We negative logged and found pOH. Flipped it to pH with 14 minus. Okay. So with this example, oxide, just a little trick, remember to make it twice the value for concentration before you pH it. Alrighty. We also have some other examples thinking about oxide as one. Hydrides do the same darn thing. And nitrides are examples of ions that can abstract protons from water. Hydride, this is a little bullet in the PowerPoint. It might look like a little O though, doesn't it? It might look like OH negative. It's not. It's hydride, H negative. Hydride is the negative ion of hydrogen. Hydro. That's an I. Hydride. If hydrogen as a negative ion, we name that ide, hydride, is placed into water, steals a proton from it, you're actually going to see little bubbles of hydrogen gas coming out. Hydrogen gas bubbles out, leaving the solution basic. Hydroxide ion is produced when hydride steals a proton from water. Here's another example called nitride. And this might be worth drawing. Let's find a spare spot. Nitrogen's Lewis dot structure, we can see that it has 5 valence electrons. And if it's going to carry a charge, we can see that it's going to want to fill those 3 open spots. When it does so, here's a poor water molecule swimming around, minding its own business. Here's a very powerful negative electron, strong enough to cleave that bond on the water molecule. Off it goes, giving me a base ion, hydroxide. So is this guy. This electron stealing a proton. And it takes 3 water molecules to satisfy this baby. 3 water molecules have now lost their hydrogens. What if we ended up making, if I take a nitrogen and add on 3 N or 3 H's? This is a molecule we're familiar with. It's called ammonia, yeah, NH3. But how many base ions did we produce along the way? Well, here was one, and here is one. We ended up producing 3 hydroxide ion concentrations. So with that example, keep in mind the stoichiometry there. Just as up above when we had to double the concentration for oxide, we'd have to triple it if we're using nitride before we calculate for pH. There's 3 open spots on the nitride ion. Each one of them is going to steal a proton, giving 3 base ions. Strong bases can be used to find something called pOH, and then a very easy flip to pH. So as we're looking at the math for strong bases, there's just a little thing at the end of flipping the pH from the pOH. All right, let's take an example of a strong base calculating pH from a concentration. Jesse, would you like to read that one for us? Yep, thank you. Gotcha. And what I was hoping we'd see is that it's just a single ion that will come out. So for every 1 sodium hydroxide mole, 1 hydroxide ion is produced. So if my value of O28 molar on the base side will indeed match the O28 molar on the hydroxide side. So it's just a 1-to-1 stoichiometric ratio. If I negative log the concentration of 0.28, we get something called the pOH, and from that we could readily flip it into pH. Kyle, would you hit with me for the pOH of our solution and just share when you're ready? Great, thank you. It's a match. Let's turn that into pH by doing 14 minus. And David, would you do that for us? Thank you. And that number makes sense. That's a very strong base, a very high pH. Alrighty. Lydia, read first the next little bullet, please. Okay, great. Thank you. So let's think about this guy, calcium, who's a +2, hydroxide, who's a -1, CaOH taken twice. When it dissociates, for every 1 calcium ion, we get 2 base ions. We're given a 0.0011 molar concentration of the calcium hydroxide. Danielle, what would be the value for the concentration of the base ion? Excellent. Twice the value. Now when I negative log, we get something called pOH using the concentration of the base. Jessica, would you share with me pOH so far? Thank you. And PJ, flip that into a pH for us. Thank you. That's what I found as well. Alrighty. So with this example, we had a 1 base come out, equal concentration. Next example, we had 2 base ions come out. So just to remember there, double the value before you pH it. Okay. Nate, let's go on to the next bullet. Share with us what's coming next here. Thank you. So thinking through our dissociation, this is a strong base, so 100% dissociates. The pH is given as 11.89, but probably more interesting than that would be something called pOH, because then I can figure out the hydroxide from that. Allie, let's do a 14 minus trick and share with me the pOH of our solution. Thank you. 10 raised to the negative 2.11 will give us hydroxide's value. Anthony, would you hit that for me? Thank you. Yep, I'll just round a smidgen. Stoichiometry says for every one base ion, we have the same value for KOH, so it also equals the concentration of our base, potassium hydroxide. Ready? One more in our series, and Ika being a reader for the little last bullet for the day. Thank you. There we go. Now, this guy, when it dissociates, and assuming that we've heated it up, we've stirred it a whole bunch, we're calling it strong, it will dissociate to release two base ions. Hydroxide ion will have a coefficient of a 2. pH is given as 11.68. More interesting, more helpful would be POH, since I'm trying to pull out hydroxide. And Riley, could you 14 minus pH and share the POH? Thank you. 10 raised to the negative 2.32 will find hydroxide for us. And Ashley, would you hit that with me? Thank you, that was fast. Gotcha. Alrighty. We were asked, however, for this guy, the calcium hydroxide, so just a little stoichiometric value, 1/2 of the answer we just found, want over given, 1/2 of 0048. And Jesse, would you share with us the concentration of the calcium hydroxide? Excellent. And that's the answer. Every one of the practice problems will deal with strong, even if it's calcium hydroxide. Assume they're saying it will dissociate 100%. In the next lesson, we'll talk more about weak acids and how they'll set up an equilibrium problem. We've got a good 10 minutes left, and if you'd like to, a couple of things. You could start your next assignment. That's pH calculations of strong acids and strong bases. You could, if you wanted, pull out your test correctives and make sure that those look good for tomorrow. A couple of things you can use your time for. I'll come around and help those who have questions, especially test correctives. You probably want to make that a top priority. I'll see if I can't stop recording.
Are the answers to the test correctives going to be online?
No, because those are actual tests, and I don't publish answers to tests. There's the key. Thanks.
I see what I would